choosing the technology. In part 1, we discussed the concept why you need in-house rapid PCB prototyping, with lousy tools even. And now let's look at different technologies for rapid PCB prototyping. Actually, there are two basic principles. How can we do? One is mechanical and the second is chemical. Mechanical technologies are PCB milling and laser etching. In both of those technologies, we are physically removing conductive layer of PCB, that copper layer of PCB. The first PCB milling, you can find a lot of DIY videos in internet, in YouTube, how to do it, a lot of different machines. And also you can find the professional machines doing that, PCB milling, then laser etching, then dry film photoresist, it's chemical, and liquid photoresist, it's also chemical. In chapter 2, we'll drill down in all 4 technologies. In reality, I would say it's 2 technologies, and find out advantages and disadvantages on all of them. In practical applications, we can't keep all of them inside. Probably we need to choose and stick on a one, what is the most universal and easiest way to implement. So here, theoretically, you can see that PCB milling is so great, so easy. You don't need any chemical process, just one small PCB machine and everything is fine in 20 minutes. In case you did PCB design, it's very easy. Everyone can do that. On a paper it looks kind of easy, but in a practice it's by far not that easy as you see. You can see this Vector.com. This is a company producing milling machines for PCB milling, and let's check requirements for such type of PCB milling. And I would like to draw attention to the tolerance of those machines. Here you can see this Vector.com website. It's Czech company, and let's look at the mills. No, let's go to home. Okay, and here you can see different versions of this milling machine, but look at the price. It's a 4,000 euro device just for PCB milling. And I also would like to draw your attention to that that device. Could we make it larger? No, that's a maximum. There are some design specifics. First, you can see solid frame, really solid frame. Vertical gantry is moving only to Z axis, massive motor, and solid table, which is moved by 2 motors. So X and Y axis are moving by on a table, and this Z axis gantry is fixed. Seems that engineers worked a lot to achieve necessary precision. Let's look at machine specifications. Okay, relatively small size, 200 by 140 millimeters milling space. 1 step of the stepper motor. We are talking about 4,000ths of millimeter. Okay, machine dimensions, not a spindle brushless motor. Special spindle, only 1 diameter of the spindle. Also everything for tolerance. We're working on 3.175 millimeter tools, and those are standards for PCB milling. Connectivity USB, it's a modern. Repeatable accuracy 200ths. It's guaranteed repeatable accuracy. It's very good, very good. It's better than 1 mil, heavy, 7 kilograms. Spindle speed 11,000 RPMs. It's not high, probably there's a reason why. Produced in Czech Republic, and PCB auto leveling option It's must. It's must. But we are talking about 1,000 of millimeter tolerance and 200 of repeatable tolerance. Guaranteed. It's not just a fake. It always should be. Probably machine is even better. Another famous prototyping equipment company, American company LPKF, yes. They're producing more advanced devices, high-speed spindles. They're starting from 40,000 up to 100,000 RPM spindles. Those are different type of spindles. Those are not just a brushless motor. They have some kind of air bearings and a lot of advanced technologies to achieve that crazy high RPMs. But they can produce PCBs at high speed. It's already manufacturing level, and you can see some machines with the tool changers. We will look at the cheapest one, Protomat E44. Let's look at specifications. Here you are. So mechanical resolution XY 0.8 micrometers, 0.04 mils. Jesus, 0.04 mils. Repeatability 0.2 mils. Very good. Precision of front back alignment 200s, 0.8 mils. Milling spindle 40,000 RPMs, pretty fast. You can go about hard to say, but I would say with at least 4 to 8 millimeters per second. Yeah, that's a good speed. Milling is just manual tool holder, fixed tool holder as well. Drilling speed 100 holes per minute. It's very fast. Travel speed 100 millimeters per second. It's fast. Yeah. It comes with a software package, and additional you can buy dust extraction unit, protective housing. What in reality is important if you're using milling as your core prototyping technology, because fiberglass is abrasive, and you don't need this abrasive dust in your lungs. It's very bad stuff. But the tolerance is a crazy tolerance. This is a crazy tolerance. So, but then you can really mill PCBs. Those are professional companies. I'm not looking even at more advanced. And then this device costs, when you have fully set, what you need will be close to 10K. Definitely, if you set a budget for 500 euros and K, it's a little bit excessive. Also, you can buy some used ones from the previous generation. Those will work, but anyway, expensive one. Hobby desktop CNC can we use? In YouTube you can find many videos how with hobby desktop CNC machines someone is making PCBs and describe the process, how it goes. Not all of them are successful. If you really look in the details, it's unsuccessful projects. The resolution is low, but anyway, maybe you can use hobby desktop CNC machines for our task to mill PCBs, and you can find them in a price range from 100 euros to 1,000 euros. Mostly those in some hobby desktop CNC machines are built from 3D printer components, and we also has one such a machine. Some time ago we bought it for a simple task. Sometimes I need to mark some holes or mill some small things for our prototypes. We have it in stock, and in this part I will look at relatively good desktop CNC machine. The price is about 400s, and maybe we can use it for our task, and then everything will be fine and it will be solved. We can do the PCB in-house manufacturing. Okay, let's measure some backlash of hobbyist CNC machine. It is relatively good machine. and I have not too much bad things to say about it, but it is basic machine. It is built from the cheap components, and I find out my worst error what machine has. In majority cases it is a better, but anyway. And what I did, I set a relatively slow feed rate and going with a 1 millimeter movement forwards and backwards to find out what is a backlash. You can see here we almost here. And here's a 500ths of millimeters guaranteed error. It's a worst case scenario. In majority cases it's even better, about a 3 hundredths of millimeters, but it is continuous error what this machine has. And in some cases you're working with a worst case scenario, in some cases in a kind of okay scenario. How to overcome it? It's relatively difficult because you need either to change for the ball screws and for very good ball screws, or there are so-called backlash nuts what are better than I have it here, and you can replace with some kind of plastic backlash nuts what you can adjust each time or calibrate each time when you need really precise operation. How those backlash compensation nuts look like? Let's see. Here you are. This is backlash compensation nut. Here is special screw. It's a plastic, and then all this backlash you regulate with that screw, and you can go to the zero backlash operation. Of course, you should do some mechanical modification, but by design this machine has about 500ths backlash guaranteed, built by design. You should do modifications. You can't operate it out of the box. Where's the main challenging? This thread is wearing out when you're operating, and then you need to adjust that backlash once in a month, calibrate your device. But this is a good solution because the cheapest possible and involves the minimum modification what you need in your design. And it is not expensive. You can get it for a couple of euros, I would say. Actually, I ordered it, and I will test it. Not too much expectations from my side. And here you can see standard backlash compensation nuts, and challenges is here. First, the tolerance still has some play, and it is okay for such kind of devices. And second one, when you mill, that spring load mechanism is not strong enough to compensate for a milling, and that means for milling you get all the backlash what you can get. So by design, this desktop cheap machine is developed with some errors, and you can't do anything about it. To improve, you need high quality ball screws, and probably not everyone knows that ball screws comes with a 10 tolerance grades, and you need a pretty high tolerance, and it is expensive. Each such ball screw, it's about 100 euros minimum. 100 euros minimum. Also, you need to properly secure it and make these additional modifications. It is expensive. So when you finish your modifications for higher tolerance, you will be about 1,000 plus budget already. And I will show you why it doesn't make sense to do all those modifications. Even you want some better tolerance. I will move it a little bit, apply a little bit force, and you can see there is additional 500s with very low effort. What I'm doing, it's not playing. You don't feel that it's playing. It's just a mechanical rigidity of machine. Here you can see this DIA machine, and the problem is here. Very thin aluminium plates. You don't feel that playing around, but by design you can easily move that flex. And where is the challenge? You can see that I remove it from the spindle, that plastic, because here's a significant vibration of the spindle. I replace it cooling with four 40 millimeter fans just to get rid of that plastic. Here it is, and this plastic has a nasty vibration. It's not very well balanced. Nevertheless, it's a relatively lightweight, but anyway, I try to reduce that wobbling of motor as much as possible. But those cheap 500 watt brushed spindles are not built with a high tolerance. We will measure it later on. And they have a vibration, and those vibrations apply to all frame, and you can't compensate that anyway. In any way, it's too easy, because normally they should not be such kind of play. I am applying really gentle force. That means all vibrations will add on additional to that backlash and other stuff. If you remember that when we looked at this check machine Baxter, it built in a different way, and also those walls was about 20 millimeter thick, I think, and country was fixed. So with hobbyist machines you can't achieve necessary tolerance. It should be different design architecture for that. But it's not bad machine. It's okay machine. You can do several things and cut wood and plastic and acrylic, and also you can drill with a high precision. For some reason, when you are drilling, all those problems goes away, and you can drill it at least with 1/10 of a millimeter, or even better. At least you will do it much better than by hand. And now let's measure spindle error. And now I set it for a tool error. A tool error, it will be even higher, because tool will be longer. I just made some optimum for measurements, and you can see -500 plus 3, it's about no, even more, plus 4, even 0.1 millimeter error on a tool, on a spindle plus collet plus everything, and that's a lot. That means if you want to go for 0.1 millimeter tool, in reality it's already 0.2 millimeter tool you should calculate, plus all errors what comes from the vibration and then backlash. I estimate that tolerance what you can get with this machine is 0.3 millimeters. Add a tool flatness about a 0.1. That means minimum track what you can make or minimum cutout what you can make is 0.4 millimeters. When you use a 0.1 millimeter milling tool, add all errors, and then you can set that tool is 0.4 millimeters. What conclusions can we make? We can make a conclusion that I think maximum tolerance what we can achieve with a hobbyist machine is a 40 mils, or it's about a 1 millimeter track with a 1 millimeter space. That would be pretty okay what we can do. So that means for some of projects we can use milling as technology as well. Let's take an experiment. This is theoretical thinking how it would work, and now I will put some practical example from industrial design, and we will look what outcome we will get from that milling option, what we will make with this hobbyist machine. And probably why I made that experiment, we should accept reality, and sometimes when we know all the tolerance requirements, we can build simple PCBs for some cases and get very fast prototype out of it, even using that milling option what we have. Or we need to buy expensive machine, and then we can do everything. And couple of words what else we introduced that to simplify all PCB prototyping process. The first one is standardization. after researching what kind of PCBs we can purchase for a reasonable money in Europe and in China, we come to conclusion that there is a universal PCB 150 millimeters long and 100 millimeters wide. You can use such type of PCB, and we mill it with this machine. That pattern, it's roughly a little bit larger than you need, but the main thing is that we use 4 screws to secure PCB, and then we mill like a reference holes with CNC machine. What it gives you opportunity to do repeatable placement on that base, and especially when you do the 2 sides PCBs, it's critical that you place it properly. So in that case, when you do the standardization, here is some holes for easy removal afterwards. Normally that part we doesn't have, and then we can slide just PCB out. It's very simple way how to secure PCB. Also, that base below is milled flat to machine. That means you have relatively high tolerance, but anyway you need that special height map for any milling to achieve necessary tolerance. Okay, let's test some PCB for industrial design. Here is an industrial design. It's around amp 10 amplifier board. Here is the top side, and they choose that top side because it contains practically all necessary tolerances to be tested. And let's look at some tracks. We can measure it. So it will be estimated measurements. You can see this is a 1 millimeter track. This is okay, 0.5 millimeter trace, and this, and the challenge or the maximum here on a integrated circuit. It's a 10 mil or 0.26. Okay, it's about a 10 mils, and between the traces we also has a 10 mils, or even less. Okay, this measurement is not very precise. It's 10 mils. It's roughly saying it's 10 mils. It's 10 mils. Yeah, of course there's a big traces and the small traces, and this is the most challenging part. And let's see what we will get out of. This is real industrial board developed by good engineers with a factory tolerance available. And then let's see what we can do with our technology, milling with a budget CNC machine. And here you can see that real milling operation. Since the spindle speed is not very fast, about 12,000 RPMs, the optimum speed is 2 millimeters per second, and this is real speed. I'm not speeding up. Most of the YouTube videos speeded up. Also we did a drilling, and let's see outcome. And here is result. It's not so bad, but what you see, definitely we can do it 10 mils. No way. But everywhere where you have 40 mils or 1 millimeter tracks and spaces, it's great. And also I want to draw your attention that drilling, nevertheless we have a backlash and errors, are precise. Those are far more precise than I can do by hand drilling. That means at least this machine we can use for drilling, especially if we register those 4 holes what I said before. We can place it back with a high tolerance, and then we can do the drilling after we process other necessary activities or processes for a PCB manufacturing. Actually, we can do it after etching, for example. Also, we can do the two sides board and keep high tolerance based on those registration pins, because the drilling is precise. At least here I have no complaints about the drilling. No complaints. Let's little bit drill down more in a quality what we can achieve using microscope, and then when we see those backlashes in a practice. Okay, this is the best picture what I can make out of it. There's some noise, but the key here is what result we got for some analysis. And we will start with a 1 millimeter tracks. Those are somewhere here. This is a mill, you can see this is a 0.1 millimeter mill, but I use it to mill those tracks, and you can see all those errors summing in roughly saying 0.3 millimeters error. So my potential tolerance using 1 millimeter mill is about 0.4 millimeters. Here is a 0.3 millimeters error in all my system, and majority of this error is coming from spindle. So I upgrade the spindle and get a better. To get a better spindle for such type of error compensation, estimated costs are about 300. You need a really good spindle with technical parameters with tolerance better than 100, some fractions of thousands. And it means not only spindle, it also means collets and collet clamps and everything. There are some crest spindles what you can use for it, but anyway, it's the next step is just this 300, and you maybe get some 0.2 millimeters better result. But that's a lot, actually. 0.2 millimeters, you know, you will be far better than you know. But anyway, it's too expensive, and it's not solving my issues anyway. Just to understand. But overall, the quality and cutting quality on an edges, everything is perfect. The depth is continuous. 1 millimeter tracks are confident. Drilling's precise. Excellent. Good. And of course, when you go to the smaller tracks, yeah, there is an issue. And here you have clearly see a backlash, and here we lost that. And let's go to closer to 10 mils, and with the 10 mils we have total errors. Yeah, nothing, everything is milled out. Machine is not ready for such task as I want to use it. But what I'm really happy, and this was my target of this test, is that the drilling is precise. And drilling is nightmare for high tolerance boards, and with this machine the drilling is, you can see, almost perfectly at center, almost perfect. I'm really happy. Even with a tiny tracks, it's by far better than you can do it by hand. And if someone is drilling instead of you, you shouldn't care about tolerance, you shouldn't care about many things. Also, we should keep in mind that those carbide drills are fragile. If you do some lousy movement, they break immediately, so you will break tons of them. And here, by using machine, I didn't break any of them. I also did tests with a 0.5 millimeter drill. It went and smooth. Excellent. And I drilled it with relatively high speed, with 6 millimeters per second. So we clearly can see that with that machine we can't make anything with a modern chipsets, and this technology is not possible unless you have a specialized machine. Specialized machine means very good tools, very precise tools. Honestly saying, it's too expensive, it's too challenging, and you need good maintenance, and you need to deal with the dust, and you need to deal with many things. And conclusion out of here is that milling technology we can keep like a backup for simple things, but mostly those DII machines we use for drilling and registration holes milling. Also, you can mill your PCB out of your prototyping board. And for comparison, let's take another example, because at the moment when I'm making this video, I made also a photolithography method. It was not polished. I just plug and play, and mostly I just roughly set some exposure times, but you can easy get a 10 mil. Yeah, those are 10 mils here. There are errors, you can see, but if I a little bit polish my process and a little bit work on exposure times and a little bit work on developer, this measuring proportions for a developer, I can achieve much better result than by milling. That's easy. It's absolutely easy, easy done. And after with the last experiment, I find out that I can drill after I have a registration holes for placing PCB. I can drill them after I made this chemical PCB development. And so it's by far more promising is going with chemical photolithography process. Is it as good as in factory? Actually, it could be as good as in factory, but the key challenge here is a film quality. In a factories, those films are for photolithography are done with a laser exposure units, and you can get a better tolerance. I'm printing on a jet printer, and still I'm impressed about the tolerance what Japan companies can make with the jet printers. It's incredible tolerance. And of course I can do better if I elaborate that chemical process.